Hey, I'm Michael, and I created a multi-agent AI system for emergency vehicle preemption. Emergency vehicle preemption is when traffic lights are controlled in a way such that emergency vehicles are given priority. Their objectives are to reduce emergency vehicle response times and also minimize the disturbance to regular traffic. Effective emergency vehicle preemption systems are capable of making roads safer for the heroes of our society, first responders. There are various types of EV preemption systems, but I chose to utilize a multi-agent system. Each traffic controller is its own independent agent. This means that multi-agent systems are highly modular and scalable while also not being vulnerable to a single point of failure. Agents are able to communicate and cooperate with each other, allowing for effective EV preemption throughout the entire traffic network, as agents are able to look beyond just their own local intersection. The holistic approach of centralized systems has also been shown to result in highly effective EV preemption. However, they lack the modularity and scalability that multi-agent systems provide. The specific multi-agent system used is called the shout-ahead agent architecture. A recent study has shown that it is highly effective in managing regular traffic, which is why I wanted to extend upon it and explore its effectiveness for EV preemption. Here's how it works. An agent first selects an action based on its own local intersection. It then communicates its intended action and attributes of its local environment to its communication partners within the agent network. Based on this communication, an agent then selects another action if a better one is now applicable. Now that we know what emergency vehicle preemption is and why a multi-agent system was chosen, let's dive deeper into the AI or artificial intelligence aspect. AI is used for agents to learn what actions to take in certain situations. This is modeled by a rule, which consists of a condition, an action to take if that condition is fulfilled, and a weight. Conditions consist of a set of predicates, which essentially describes a situation. If all the predicates are fulfilled, then the condition evaluates as true, making the rule applicable. The actions that a traffic controller can take are simply a permutation of phases for each of the traffic lights that it controls. The weight is a numeric value that represents the quality of a rule. A higher weight means a better rule, which makes it more likely to be applied. So that's a rule that models the behavior of an agent. Agents are made up of a collection of rules. More specifically, these rules are split into two categories, a local rule set and a cooperation one. Reinforcement learning, or more specifically, the SARSA algorithm, is used by agents to learn within its rule set which rules are best. From the applicable rules, one rule is chosen to be applied. This is done by looking at the rule weights, but a probabilistic function is used in order to balance exploration and exploitation. The action for that rule is then applied. If something good happens, for instance, letting an emergency vehicle through the intersection, then the weight of the rule will be increased. On the contrary, if something bad happens, the weight of the rule will be decreased, making it less likely to be chosen in the future. To determine specifically how the weight of a rule should be updated, a reward function is used. It takes into account throughput, queue difference, change in the leading EV speed, change in the queue length ahead of the leading EV, and a penalty is applied if it causes an EV to stop. So that's how an agent learns within its rule set which rules are best. To diversify the rule set with different rules, an evolutionary algorithm is used. Each agent has a pool of individuals, and each individual has a unique rule set. Within a generation, different combinations of individuals are put together in runs, in which they cooperatively manage traffic and preempt for emergency vehicles. At the end of the run, all individuals receive a fitness score, which represents how well they performed. After all individuals have participated in at least 3 runs, the generation is complete and evolution occurs in order to create a new generation. Based on the fitness scores received by the individuals, the best individuals move on to the next generation. The top individuals are also bred together, in which their rule sets are combined with a likelihood of mutations. And unfortunately, the worst individuals don't make it on to the next generation. A fitness function is used to determine what qualifies as a good or bad individual. This function takes into account the parameters of simulation time, aggregate vehicle wait time, average EV speed, and the total EV stop time. To learn a balanced EV preemption system that has a minimal disturbance to regular traffic, two variants of the local and cooperation rule sets were learned. The difference between the two rule sets lies in the predicates that rule conditions can consist of. All of the predicates for each rule set are displayed in this table. A layered learning approach was used to learn these two rule sets. First, regular rules were learned using reinforcement learning and the evolutionary algorithm. Then, the emergency vehicle rule set was learned on top of the regular rules. What this looks like is if, at any instance, no EV rules are applicable, then the agent will look towards the regular rules that have already been learned and apply an action from an applicable rule in order to change the state and hopefully make more EV rules applicable in the future. This entire project was implemented using the Python programming language and integrated with the Simulation of Urban Mobility, or SUMO, simulator. In brief, I created a multi-agent AI emergency vehicle preemption system by extending upon the shout-ahead agent architecture. To the best of my knowledge, this artificial intelligence and multi-agent system approach towards emergency vehicle preemption is novel. To achieve this, 4 primary extensions were made to the base traffic management system. Emergency vehicle rule sets were created for the local environment and the cooperation environment. The reinforcement learning reward function was modified to take into account emergency vehicle parameters so as to learn to prioritize emergency vehicle traffic. A similar change was applied to the fitness function for the evolutionary algorithm. And finally, to learn a balanced system, a layered learning approach was used. To evaluate the performance of the newly created multi-agent AI emergency vehicle preemption system, it was compared against 3 other traffic management systems. The complete system consisted of emergency vehicle and regular rule sets for the local and cooperation environment. To gauge the importance of cooperation, the system was tested against just the local emergency vehicle rule set. Next, the base system, without any emergency vehicle preemption capability, was used as another system variant. And finally, as a control, all of these systems were compared against SUMO's actuated traffic light algorithm, which is just a really simple mechanism that is used for controlling traffic lights. The system configurations were tested on 50 varying traffic flows in order to obtain a sample of the system's overall performance. But before we get to the graphs, let's take a look at the system in action. On the left is the complete system, and on the right is the system without cooperation capabilities. Now this part's really interesting. You'll see that on the left side, emergency vehicles are going to be prioritized far more than the right side. And now you'll see that on the left side, as soon as that last fire truck passes through the intersection, the rest of the vehicles waiting vertically are going to be let through. Visually, this illustrates that the created multi-agent AI system is highly effective at EV preemption and also minimizing the disturbance to regular traffic. So now let's look at the numbers. The first metric is the average emergency vehicle speed, in which a higher value is better. Quite clearly, you can see that the complete system on the very left outperforms all the other configurations, and the system configuration without cooperation performs the worst, while the other 2 systems are essentially the same. The total number of EV stops, in which the lower the better, tells a very similar story. However, it appears that the non-cooperation configuration appear relatively better. The simulation time is a metric to gauge the disturbance to regular traffic. Just like the other previous metrics, the complete EV AI preemption system performs the best. And finally, this graph illustrates the learning progress over generations. The positive trend line validates the usage of AI because the agents are becoming better over time. average EV speed, and total number of EV stops are excellent indicators of an effective EV preemption system. The final conclusions that can be drawn from this is that multi-agent AI systems are effective for EV preemption and minimizing the impact to regular traffic, and agent cooperation is extremely important to their success. These insights can help reduce emergency vehicle response times and consequently make communities safer for everyone.